So in this video, I want to demonstrate how the Marble Machine X can be quickly programmed by converting MIDI files into CAD-based 3D projection. So here's how. So before we get into it, let's do some quick math just to define the scope of the issue that 3D projection can potentially help solve. So the Marble Machine is comprised of 19 instruments. There are 11 interchangeable vibraphone plates, a crash cymbal, a bass drum, a snare drum, and a hi-hat, and 4 bass guitar strings. However, each of these 19 instruments have 2 marble lanes pointed at each of them for a total of 38 marble channels. Now, the Marble Machine plays 16 measures of 4/4 time, or rather 64 beats. So if you were to count musically 1, 2, 3, 4, 5, you would get to 64 before starting back over at 1. So how many notes then are there per beat? Or how many different positions are there for any of those 64 beats on a channel? The answer is 10. So the middle row, we have 16th notes. So 1E end, a 2E end, a 3E end, a 4E end. And on the left side here, you can see 32nd notes. Those are just notes that go in between the 16th notes for increased time. So for a given beat, 1, 2, 3, 4, there are actually 8 of those positions that are equally offset from each other. And on the right side, you have the triplet row. Now there's only 2 triplet positions per beat. And the reason for that is because they share the downbeat that you can see here at the bottom. So if you went triplet, 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 or 1 triplet, 2 triplet, 3 triplet, there are 3 notes per beat, but they share the downbeat. And then the other 2 notes are here on the right side. So what we know is we have 38 channels that plays 64 beats a piece, and of those 64 beats, there are 10 positions per beat. That gives us the math 38 times 64 times 10 equals 24,320 holes in the programming wheel. Now that doesn't include the mounting holes that you see, all these silver fasteners that hold it to its substructure. And you can see that there's a row of 32nd notes missing because of the seam. So there would be this row here, you could see that there would be a note here. So you could subtract 38 32nd notes per seam. And I believe that there's 4 seams. So 38 times 4 would come off of this total here. All right, so we know that there's about 24,000 positions where programming pins can go in the Marble Machine X. And a song could be composed of hundreds, if not thousands, of programming pins. So what this experiment aims to do is we're going to compose a song in MIDI using a DAW, like Ableton Live, or I think Martin uses Logic Pro, anything like that, where we can actually write a song in MIDI and very quickly edit it on the computer and see if we can take that MIDI information and then export that and translate that directly into an overlaid projection right onto the programming wheel, so that we take our MIDI and we just bring it to life directly onto the programming wheel. So we're going to do that using a software suite called ProjectionWorks. And this is how ProjectionWorks works. So ProjectionWorks is a tool that allows a manufacturing engineer to import a CAD model and then sort of overlay that CAD model with all kinds of text and images and relevant positional data to help a technician on a shop floor assemble some typically large, complicated thing. It's mostly used in aerospace manufacturing, where, say like in the assembly of airplane wings, where you might have thousands and thousands of fastener holes that need to be filled, but with all kinds of different part numbers and different lengths of fasteners, where there'd be a lot of manual counting and referencing of drawings. But if you could just overlay sort of, okay, take part number ABC and put it in these 70 lit up holes and then move on to the next one, you can imagine how much time you could save with something like that. The Marble Machine sort of is faced with a similar problem, that you have 24,000 holes in the programming wheel, but only some of those holes matter in the context of the song that we're trying to play right now. So anyway, to do a demonstration for what this would look like on the Marble Machine programming wheel, we're going to use this cylinder here. I've got a real life cylinder that matches this CAD model. So just to show you some CAD data here. Oops, that's the inner diameter. So the outer diameter is 774 millimeters, and the cylinder I think is about 1,200 millimeters tall. So I think it's a little bit taller than the Marble Machine programming wheel, with maybe a slightly smaller diameter. But anyway, we're going to use this to sort of demonstrate how 3D projection works on something like this. So moving over to the projection software, we're going to take that CAD model that was generated in, whether it was CATIA or SolidWorks or some professional CAD package. So we're going to import that piece of base geometry, we'll call it. All right, so here's our cylinder. You can see it's got all of these holes in it. And so coming out of that same CAD package, we would know the position in XYZ of all of these hole locations, and we can get a normal vector for them as well. So I've went ahead and exported and pre-formatted a CSV of all of these hole locations. So we get a feature type, a unique ID for each one, a part number of, like, say, what fastener is being installed, and the important part is an X, Y, and Z position in space, and then, of course, a normal vector component, so an IJK, essentially, like what is the direction that this point in space is pointing if you drew an arrow coming out of it. We're going to import a 1-to-1. This solution is in millimeters, and so now we have these finite points in space, and we're going to draw some kind of shape around it. So we could draw a circle, rectangle, triangle, diamond, something like that. We're going to draw a circle. Let's make it a blue circle here. And we'll make that circle have let's say like a 7 millimeter diameter. And then the line color and the line width, we'll do like a 1 millimeter sort of yellow ring around that. We'll press OK. Now these circles come in backwards because I've got my normals flipped by mistake, but I can select the entire collection. I think there's 500 points here. You can select the entire collection. I'm going to reverse those. There we go. Oops. So now you can see where all these holes were. I've got a blue circle with a yellow ring around it. If I click on any given one, I can see its name and ID and some other attributes about it we can use to sort and project this content in real life in the field, to say, show which holes are what kind of part number for what fastener. So let's quickly create a job here and then project it on the cylinder, see what that looks like. So I'm going to click on this cell here. I'm going to call it MMX position 1. And got to create a job. So we'll call this MMX assembly demo and add a general installation task. So we're going to add everything that's shown here in the task, so all of the data that's currently imported, and we're going to sort it by part number. So sorted by part number, and that's it. Going to hit File, Publish, and down here we see that the job is published, and that's it. So in just a matter of minutes, we can import some CAD data, overlay it with a CSV that was generated from that same CAD package, and then now we can project that in the real world. So let's have a look at what that looks like. All right, so how do we align the projector in the real world to the CAD model and the project that we created in the editor software? So this piece of software right here is going to help us do that. So we're going to open a template. So we see we have an MMX as the target, and then we're going to use the MMX alignment master demo here. And so that brings up the project that we had before, and we're going to select our projector. So in this case, our projector's name is PV-22476. And now we just got to go through a couple of steps. We're going to do a setup, take a picture. And so this is a picture that we have a camera bolted to the projector, and this is what it sees in the real world. And we'll apply some feature detection to it that might be useful to us. And we'll just press OK and hit acquire. So the way that the software works, it does a white light scan, which gives us a composite computer-generated view through the projector's perspective, not the camera's perspective. So it kind of creates a stereo vision effect by using this white light scan. So as soon as it's done, in the bottom of our software here, now we get basically all of the projectors coming out. This is a 4K projector. All of the pixels that are coming out of the projector are now represented here in this composite image on where those rays actually trace to based on the projector's perspective. So the way that we align the projector is we just need to teach it a couple of things about what it's looking at, make some links in CAD. So we can see these ovals here, for example. So if I zoom in, so okay, maybe this one's a little bit off, but I can create a link here and say that this link in space is this clickable point in our CAD model from the project that we exported from before. So we're just going to do that 6 times. So we need a minimum of 6 points in order to create a perspective. And when that's all said and done, it looks like this. So once we've made enough links, we register the projector into or bucket into the coordinate system of the actual geometry, the physical model of the thing that we have a CAD model of. And now we can essentially project whatever we want to. So in the case of the marble machine, we would actually be using the programming pinholes to align a projector to it, and then we would project over those holes, much like we would be using these holes here to tell us what fasteners we're going to put in these holes. But because we're now aligned to this cylinder, I can now project other content like a simulation of the marble machine data. So now moving on to the shop floor side of the projection demo, we're going to take that job that we published, that MMX demo, MMX assembly demo, and we're going to give it a name, a serial number. We'll call it demo 1, and we'll hit create. So inside that job, we have our series of tasks. In this case, we only have one, installation task 9. Jumping back over to the editor, actually didn't rename that task. So when I created that installation task, it's just called task 9. So we could rename that here if we wanted to and republish it, something like insert programming pins or something like that. All right, so now we should have a CAD preview here that we can manipulate that shows us what should be projected. And on the left side, we have a list of steps because we programmed it to break it out or group it by part number. So we have 57 of these around the cylinder, part number 2, part number 3, part number 4. And what we see in the CAD preview should be represented in the real world on the cylinder. Part number 5, 6, 7, 8, 9, and 10. Now, the reason that we have these part numbers 1 through 10 is actually in the CSV file. I actually just used an Excel formula for the part number, and I just gave them a random value. All these positions around the cylinder, gave them a random value between 1 and 10. But a part number can be any alphanumeric string. So it could be XYZ 1, 2, 3, or part number, fastener AB, whatever. So it's a nice way we can just group things that matter against things that don't matter for any given view that we want to show at a given time. Okay, so now you've seen how we can import a CAD model and a corresponding CSV file and overlay it on top of that CAD model. And we need some relevant features in order to align to that CAD model. So in this case, obviously the holes that are in the cylinder allow us to align to it. And once we're aligned to it, we can really put anything into that coordinate space that we want to. So to prove that we can convert MIDI into something that's useful on the marble machine programming wheel, I created a CSV here based on what I know about the cylinder that I have and what I know about, the math at the beginning of the video of the 38 channels and the 64 beats and the 10 hole positions. Was able to create a CSV that has all 24,320 positions around this cylinder. So what that ultimately looks like is this. Now, there are some things that would be a little bit different. Obviously, the barrel height, the cylinder height and the cylinder diameter is a bit different between them, but you can see generally that the pattern is effectively the same. So there are 38 MIDI lanes wrapped around the cylinder that represent the same positions geometrically in space that would be used on the programming wheel. So what does this look like projected onto the cylinder? And so here we have it, a emulation of the Marble Machine programming wheel in projection. So now that we know that we can project around a cylinder all 24,320 points, now we need to prove that we can take a song in MIDI coming out of a DAW and quickly filter it by these known positions and project just those positions. So tying it all together, let's do that now. All right, so let's tie this whole thing together. So you've learned how to import a CAD model and then a CSV and then align the projector to the real world as-built model of that CAD model. And so now we want to see, can we create a song in a DAW? So here I'm using Ableton Live. Can we create a song, export it as a MIDI file, and then turn that MIDI file into projected programming pin locations on the Marble Machine programming wheel? So let's start here with a familiar vibraphone MIDI file. And we're going to take this file, we're going to export it, and then we're going to translate it into spatial coordinates and then project it. So let's give that a try. So here's the vibraphone part you can see, and I'm going to right click on it and export it as a MIDI clip. I've done this before, but we're going to call it vibraphone.mid. I'm going to just write over it. So there's our MIDI file. All right. And so I found this really cool MIDI to XL converter online. It's open source. I'll put a link in the description. Super cool. But it's just a macro enabled workbook in Excel. So I'm going to press the start button. Here's that vibraphone.mid that we just exported. And so now we have a MIDI version of the Marble Machine vibraphone part. And it gives us a couple of things that we need. It gives us the time in ticks, and it gives us the event, which would be a note on, which would be where programming pins go. It gives us the pulses per quarter note, which shows the resolution of the MIDI file. And it gives us the note number. So what key on the piano essentially was played. So what we're going to do here, I'm going to click here in the corner and I'm going to just copy all of this content, because pasting it in this workbook is, as I've had problems with it. So I've got this other template that I made where step 2, click in cell A1 and paste the copied content and proceed to step 3. So I'm going to click here and I'm going to paste. Okay, so now we've got that same imported content here. And then now we're going to go to step 3. All right, so step 3, sort column C from smallest to largest. Then using this table, convert each MIDI note number to a Marble Machine X channel by entering a channel value from 1 to 38, and then proceed to step 3. That should say 4. Okay, so column C is the note number. So I'm just going to click sort smallest to largest, and this is an Excel formula called unique. Super cool. It's going to search all of the notes that were played in this song and return only unique values. So, and then it spills over downward. Super duper cool. So we know that keys 71 through 88 in ascending order were played. And actually, if we look in Excel, you can see the count is 11. Well, we know that in the original Marble Machine song, there are 11 vibraphone plates, just like the Marble Machine X has 11 vibraphone plates. So we want to just take these piano notes that were played, doesn't matter what they are, and we're going to convert them into channels 1 through 38. Now, if we wanted to, we could say all of these are going to be channel 1. We're not limited to, they don't have to be unique. We could say dump every single track down the same marble lane. But because we know these are all going to be different vibraphone plates, let's put them on, say, even numbers. That way we're skipping 2 channels at a time. Okay, so channels 2 through 22 are going to be our ones that we're actually going to use for this song. So then we'll jump over to, no, this should be called step 4. But we're going to jump over to this table here, And this used to be step 3, I promise. So step 3, filter column O to show only the values of 1. Then copy and paste this filtered table into a new workbook and save it as a, that should say CSV, comma delimited. Okay. So now we're using, in this case, a VLOOKUP function. It's going to take, so here we have a table that's got all 24,000 positions, right, on the marble machine. But now we're going to compare this table to this one here, where we actually had a hit on a song. So is used in song, just got it to be binary here. So we're going to say, just show me the ones. And now we can copy this table, and just to keep it nice and clean with no formulas, we'll open up a new workbook and we'll just paste it as values. And so now if we go down to the end of this table, we got 130 rows. So there are 130 programming pins that make up the vibraphone part on the Marble Machine X for the original Marble Machine vibraphone part. So let's save this. Save this into MIDI converter. And we'll save this as vibraphone demo, and we'll save it as a CSV. Okay. So here we've got our cylinder. This is a template that I created. We're just going to change the name of the song. We'll call this song Marble Machine 2016. Import. And we'll go into MIDI converter, and there's that vibraphone demo that we exported. Oh, it's not ready for reading because I've got it open. So I'm going to close it. All right, part number, we have to give it a value here, so we'll just call it point, doesn't matter. Okay, and in this case, we want to make it, I'm not exactly sure what the size of the holes are, but we're going to do rectangles. We're going to say they're 4 millimeters by 2 millimeters with no angle and no line drawn around them. Okay, so now that we've got our vibraphone part loaded onto our digital programming wheel here, we've got all of our positions here that you can see wrapped all the way around the barrel. We are going to publish this. And then we'll open up the shop floor software. And we're going to create a new one. There's that MM2016 is the name of our song. And we'll call this Demo 2. And insert the programming pins. So as you can see here, the MIDI file that you see in Ableton matches pretty closely to what you see projected on our programming wheel emulator here. So obviously I don't have a programming wheel here. I don't have a marble machine, so I can't actually test to prove that it works. But the software is doing exactly what I've told it to do, and if my calculations are right, this should actually produce it should actually tell us where the pins go and produce the song that it is intended to produce. Now, alternatively, if you don't want to see just the projected locations that matter in the context of the song where the pins go, but you want to see, well, everything, we could choose to not filter this row. And then we have a table that is all 24,320 positions. Now, if we copy this table, okay, it's a much bigger data set, so it just takes the system a little bit longer to process it, but we have this variable is used in song, and I'll show you how we can sort and make this a different color so that we can still kind of see everything in context. So let's save this as, we'll save this as comma delimited, and we'll save it as vibraphone 2. Okay, so I'm going to jump back into our project here. I'm going to delete out that CSV where we imported that song. And now we're going to import vibraphone 2. and it is open, of course. Vibraphone 2. Part number, we're going to call it a point. And we want to check this box here, is used in song. We want to import this column as well because we're going to use it inside the editor. And we're going to make rectangles. We'll make them 4 millimeters by 2 millimeters. Make that 0, and we'll say OK. Okay, so here is all of our points again, but and actually I made them yellow. Let's make them be a color that's a little bit harder to see. So we'll make them be like red. And then we'll make so now we want to use a selection form. We're going to make the points that we want to see, we're going to make them stand out and be yellow. So we want triplets, beats, and offbeats where is used in song equals 1. So I do that form there. You can see some of these lit up. I have selected 129 items. And what we want to do now is down here under fill color, we'll just make them be yellow. And just like that, you can see where all of these pins go in the context of the patterning that we would see. So we can project all of this on the cylinder if we want to, or we can project just the ones that we had before. The system will be much more responsive if you're only projecting 100 points versus trying to project 24,000 points in space, but effectively gives you the same information. So really we only care about the yellow ones, so we don't really need all these red ones, but if you really wanted to see them in the context of the rows and all of its neighbors, then you could do it this way as well.